So today I'm going to talk about Boyle's law, that what is Boyle's law and the parameters of gases first of all before discussing the Boyle's law. Right, so now I'm going to talk about Boyle's law. Before moving ahead, because Boyle's law, we know that the gases have four values. Gases do have four variables. That is temperature, temperature, wait, temperature, pressure, volume, and mole. Right. So these four parameters that we consider in gases, right? Pressure, temperature, volume, and number of moles, right? Moving ahead to discuss it, I would like to tell you this thing that volume in Boyle's law, volume is inversely proportional to pressure. If you consider Boyle's law, that is inversely proportional to pressure. The Boyle's law states that, which means that if the volume increases, the pressure decreases. That we can see here practically as well. For example, this is a gas molecules. We have provided no temperature and anything. The gas molecules are spread all over the container, fighting with the wall of the container, or maybe pressure is they are creating pressure, volume, what so we are not considering that right now, right? So for us, pressure and temperature, pressure, here we have a constant number of moles and temperature is constant for a while, right? But if if the volume increases, as you can see that volume increases, pressure of gas molecules decreases. Here the volume decreases, pressure of gas molecules increases. As you can see, the molecules are spread all over the container here, but here we have, we have applied a pressure due to which the gas decreases, and they are compactly they will take a shape, or there's something else, compressibility factor z equals to 1, that's something else that I'm not going to discuss here. But here one thing that we have to consider here, that when the volume increases, pressure decreases, and the pressure decreases, volume increases. This is basically a Boyle's law, and we know that if volume is inversely proportional to pressure, then one thing that we have to consider here is that when we remove proportionality sign, we get constant, right? So this is something like this. Okay. So this k is basically a constant here. This k is a constant. This k is a constant here, and k depends upon unit of pressure, volume, and temperature and molar number of moles. Okay, the k is dependent upon these parameters, right? If we say that at constant temperature and number of a constant temperature, the volume and pressure of a gas is volume, pressure of gas molecules are V1, V1 and T1. Okay, this is a pressure, initially pressure and volume, and after changes, maybe the pressure has changed, maybe the temperature has changed, it becomes sorry, it become V2 and T2. Temperature, this is, so we can write it like this as well. It can be written here as like this as well. V1 plus V2 T2 is equal to constant. This is also a way of writing the Boyle's law equation. Now after that, I would like to discuss the graphs here of pressure and volume. Different graphs, right, according to different conditions. Okay, different graphs, right? Okay, let's go. So the first one graph here, graph number 1. First, before drawing graph, graph number 1, I would like to write some equation. We know that volume is directly proportional to inversely, I'm sorry, inversely proportional to pressure. Then volume is equals to K 1 upon V. Wait, K upon V. Then P. This is P. Oops. Let me write it again. No problem. By drawing the graph, we have to consider certain things, that volume is inversely proportional to pressure. It's a pretty confusing term, no? Volume equals to K 1 1 upon B 1 upon T. PV is equals to constant. PV is equals to constant, and PV is equals to K. So this is the parameter. These are the parameters that we have to consider, or maybe we're gonna use while drawing the different graphs. First graph is a relation that that pressure is inversely proportional to volume. After removing the proportionality sign, we have a term which is K 1 upon V. So what will be the graph? Let's see here. Let's see. Okay. So I would consider I'm sorry. We know that this is a graph. Okay, you might notice that this equation is something like this. Kx is equals to y is equals to mx. This equation is something like this. Y is equals to mx, where y pressure represents y, x we have volume, and m represent K. M here is basically a slope which originates from the origin, is something like this. K. But what does mean by K here, right? So let's see what mean by K here, right? We know that PV is equals to nRT. PV is equals to constant. So constant, right? So C is equals to number of moles is constant. Gas universal gas law, the gas constant is constant. So K, which means constant, is directly proportional to temperature here, right? So here the K representing temperature, and it means theta, tan theta, right? It shows tan theta. Tan theta. Now we can consider graph with different temperature, because K represents state, T and means theta, right? So let's consider different graphs on different temperatures. So let's move here. Okay, let's go. For example, we know that this is a graph where we have a different temperatures here, like T1, then T2, then T3. This is T1. Wait. 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 This is T3. Then we have T2. Here temperature 2, and this is T3, right? This is T1. I'm sorry, I'm mistaken. So, okay. Oh, my mind, I'm mistaken. Then we can easily this by this is T1, T2, and T3, right? So this is theta 1. We know that the theta means tan theta, theta 2, and theta 3 here. Temperature. Here we have you can take volume either here or there. It's your wish, right? Universal pressure, right? So we know that the tan theta. So as the temperature tan theta increases, volume the value of